This video will provide you a basic understanding of the element types and meshing in 3DEXPERIENCE. It is specifically tailored for someone who is new to performing structural analysis. 3DEXPERIENCE contains a large number of different element types that you can use for modeling structures. By examining the behavior of some common objects, we can better understand when you might use a particular 3DEXPERIENCE element. First, we will examine the trailer hitch. More specifically, we will focus on a single component, the slotted lug. The length, width, and height of the lug are all of the same order of magnitude. The lug contains a slot and 3 holes. It also contains a number of chamfers and fillet radii. For parts like this, tetrahedral elements are a good choice. 3DEXPERIENCE has both 4-node and 10-node tetrahedral elements. The 4-node tetrahedral elements are also called linear elements, and the 10-node tetrahedral elements are also called quadratic elements. 4-node elements tend to significantly overpredict the stiffness of structures and should only be used as a last resort. When meshing a part in 3DEXPERIENCE, you need to select quadratic elements. There are 5 types of quadratic tetrahedral elements in 3DEXPERIENCE. The mathematical formulation of each of these elements is slightly different. The C3D10HS element is the default tetrahedral element type. While this element requires a longer solution time than some of the other elements, it is a great element to use when you are first starting to use structural simulation. We are now ready to start discussing how many tetrahedral elements we need in a model. Generally speaking, we use larger elements in non-critical regions, and we use smaller elements in critical regions. But how do we identify a critical region? The critical regions of a model are typically along the primary load path, where the part contacts another part, and in stress concentrations. Stress concentrations typically occur where the geometry changes significantly, like at holes or corners. Before investigating the critical regions of this part, we need to explain a bit about the design. There is significant clearance between the highlighted surfaces. This causes the load to be transmitted between the 2 parts, through the lock pin, and these faces. However, when pulling the trailer, some load may also be transmitted through these surfaces. And side loads are transmitted between these surfaces. The holes in the lug meet all 3 criteria for critical regions. A good practice is to use a minimum of 12 elements around the circumference of a critical hole. There are small fillets in the slot. These regions are along the primary load path, and are also a stress concentration. Generally, we want at least 4 elements in a fillet like this. We currently only have 2 elements, so we will likely need to refine the mesh in this region. The side of the lug behaves like a beam, and is along the primary load path. Generally, we want to have at least 2 to 3 elements through the thickness of a feature like this. One of the quickest ways to identify the critical regions is to run a model with a relatively coarse mesh. This model is quite coarse, but will solve quickly, and will help us identify the critical areas of the part. We can quickly see the highest stresses occur in the hole, where the pin contacts the lug, and on the edge, where the lug contacts the adjustment bar. If we set the maximum value of the Van Mises stress contours to a relatively small value, we can also quickly see the regions of the model which are located in the primary load path. Any region colored red is in the primary load path for the part. We can apply the knowledge gained from reviewing the results from the coarse mesh and the general recommendations to design our mesh for the lug part. The locations of highest stress have not changed. However, the peak stress has increased from 393 megapascals to 908 megapascals. The second item we will examine is a cardboard pizza box. This box has very thin walls when compared with its other dimensions. It would be very inefficient to model this box using solid elements. Fortunately, we can mesh the outside face of the box with 3-dimensional shell elements. 3DEXPERIENCE has both quadrilateral and triangular shell elements. Elements with 3 or 4 nodes are linear shell elements. Elements with 6 or 8 nodes are quadratic shell elements. Like the tetrahedral elements, some shell elements have limitations which can significantly impact accuracy. If you are new to structural simulation, the best approach would be to use either S4 or S4R elements. It is okay to have S3 or S3R elements mixed in. But try to create a good quality mesh with 4-node quadrilateral elements. So, what is a good quality mesh? The ideal mesh consists of perfectly square elements. One can rarely create a mesh consisting of only ideal elements. There are a number of shapes to watch out for. Most meshes will contain some elements that look like these. The key is to limit how much they deviate from the ideal shape, and to limit the number of misshaped elements. Fortunately, 3DEXPERIENCE includes a tool for us to check the quality of elements. If all elements are coded green, the element shapes are acceptable. However, that does not guarantee that the mesh has been adequately refined. In addition to regions of high stress, we also need to consider the curvature of the shell surface. To explain this, we will examine a simple circular shell structure. If we mesh this surface, and check the mesh quality, all of the elements appear as green. However, we have not adequately refined the mesh along the circumferential direction. If we run a simulation using this mesh, the structure will act like a structure with 4 distinct folds, rather than a smooth circular shell. To represent a smooth surface, the difference in the normal angle between elements must be less than 20 degrees. 3DEXPERIENCE does not have an automated tool for checking this. However, you can manually measure the angle between the element faces. If the angle is too large, modify the mesh parameters and remesh the part. The final item we will look at is the cable used to change the gears on a bicycle. The shift cable behaves like a long thin beam. So, if we are designing the shifting mechanism, we might model the cable using 3-dimensional beam elements. 3DEXPERIENCE has 2-node linear beam elements, and 3-node quadratic beam elements. If you are new to structural simulation, use the quadratic beam element, B32. At this point, it is worth pointing out that modeling the cable using beam elements was one of many choices that we could have made in our 3DEXPERIENCE simulation. The shift cable is actually a bundle of other cables, very similar to this. If we were particularly interested in what happens to the cable, we might have modeled the cable in more detail. We could have modeled each individual wire in the cable, using beam elements. Or, we could have gone to the extreme of modeling each wire with solid elements. Modeling the cable requires a high level of expertise. Do not attempt this if you are new to structural simulation. If you need to model a component like this, then you should study the topics of nonlinear analysis and contact. Using 3 everyday objects, we have introduced you to the element types that you will use for structural simulations in 3DEXPERIENCE. We also provided you with recommendations on mesh refinement and element selection.